Hey, good morning all. Welcome to Storage Developer Conference 2022. My name is Rakesh. I'm currently working as a Customer Success Manager for the Asia Pacific region for VIAVI Solutions, one of the leading manufacturers of the test and measurement equipment in the world. Let me start my presentation. So hope you all see the screen. So today I'll be presenting on the protocol analysis for the CXL.
Let me start with the overview of the presentation. The presentation focuses or highlights on the VIAVI analysis capabilities for CXL with added focus on the CXL 2.0 specification. Difference between earlier specification revisions will be identified. VIAVI Xgig tools for analysis and debug CXL operations will be shown. The targeted audience would be those who are familiar with the PCIe protocol and the implementation, those who need knowledge of the new CXL protocol, those who expect to debug CXL communications and the devices. In terms of agenda, here I will talk about 5 minutes on the CXL and PCIe ecosystem overview, 10 minutes on the CXL primer, 15 minutes on the CXL protocol overview, and 10 minutes on the CXL protocol analysis system. Okay, let me start the presentation. I would like to do a brief look at the PCI Express and CXL history and the ecosystem for CXL as it stands today. So looking at the slide across the top bar here, the CXL was introduced in March of 2019 with the version 1.0. It was quickly updated to the version 1.1, which was mainly some simple clarification and not much change to the actual protocol itself. However, a year and a half later, CXL 2.0 was introduced in November of 2020. That was a significant upgrade. It did include a new feature such as link switching and switching devices, where to find a link security was added. And there were a large variety of miscellaneous updates and clarifications. And of course, the CXL supports full backward compatibility to CXL 1.0 and 1.1 was added, just like the PCI Express. Today, we are looking forward to the release of CXL 3.0 sometime this year. The important message here is though CXL protocol has been rapidly expanding and adding a lot of features. Moving on to the second line of boxes here and taking a look behind just the standards themselves is the new engagements in the industry. So it was April 2019 that Intel announced the FPGA product that had CXL support. About 6 months later, the CXL Consortium was incorporated in September 2019, and we have started working on our own CXL decoders. And around that time, and 6 months later, we introduced our first version of the CXL decoding or analyzer solution. And then moving over to the left here, on May of last year, 2021, the first real product was announced. Samsung announced the memory module with CXL interface on it. But if we look at this now, today there are no CXL devices available off the shelf. Multiple vendors have the products under development, but they are not available off the shelf for the purchases. And the ecosystem who are working on the CXL includes IP suppliers, IC manufacturers, system and subsystem vendors, and the software developers. So now that's the CXL ecosystem from a high-level point of view. Let's take a quick look at the CXL Consortium. Today, there are approximately 170 plus members in CXL Consortium. The board of directors is 15 from the industry's leading companies. I think you'll recognize all of these things here. And then simply I did not have any room to put all the remaining 155 members in the list. But I did want to highlight many of the important companies, and the VIAVI, of course, in yellow at the bottom. So that ends my overview. I would like to move on to the CXL primer. Compute Express Link is a communication protocol that's intended to enable much faster communication between CPU to devices and memory. Its advantages are remote memory access, efficient resource sharing. That means, these features are all targeting the application of artificial intelligence and machine learning. And what's closely associated to that is persistent memory as well. So it is a specific set of applications that excel well, provided the most benefits. CXL actually is designed to operate on the PCIe Express 5.0 physical layer. So you got an electrical signaling running at 32 giga transfer per second and link width up to 16 lanes. It's interesting that CXL actually uses PCIe 5.0 alternate mode of operations called FlexBus mode within the CXL standard. But it's this alternate mode that allows the system to boot to a PCI Express and transition into CXL mode using a FlexBus functionality. And that's somewhat shown here in the diagram on the left. You can see CPU has both the CXL and PCI Express protocol function, and they're ported over to the link, what's termed the FlexBus port here, so it can run either PCIe or CXL. CXL moves data in terms of 528-bit flips, and a flip is a flow control digit or a flow control unit. More on that later. Why CXL and why CXL 2.0? The main benefit, as I mentioned, is to improve performance, but in system with proper implementation. It should also allow for reducing complexity and even system cost while improving your flexibility. To do that, CXL defines coherency to enable memory pool that are consistent in terms of validity of data that allows more efficient and faster resource sharing between devices and processors. The second major benefit is heterogeneous nature or heterogeneousness. CXL is very unique. Most protocols require virtually identical processor to be able to communicate, but CXL does a lot different processor types, different processor versions, generations to all share a same fabric or infrastructure. And the benefit of that is that you can build the system today with available components and then the future be able to update it with the newer components that are even faster and better. And this also had a significant benefits to the AI and machine learning application. When you compare that to PCIe, of course, there are pools of memory within CPU. The main host CPU has one or more, and the graphic devices has many. But those memories are isolated. That's very hard to get sharing done between them. When those memory are, when you're able to share those resources, it's inefficient, slow, with high latency. And CXL 2.0, which addresses most of those issues now, while also adding a benefit of link fan out for expandability and security. Both are important additions compared to the PCI. As I mentioned earlier, that CXL 1.0 and 1.1 were very similar, and here is a chart shows differences in generation. And if I jump down here to compliance towards the bottom of the list, you will see that the one significant addition to 1.1 is some definition to prepare for compliance testing, and interoperability testing was added to the standard. But prior to that, both of them offer the 16-lane 32G of operations as maximum. They both support FlexBus and offer coherency. There are three sub-protocols defined: CXL IO, CXL memory, CXL cache. I will talk more about this in just a minute. Both CXL 1.0 and 1.1 supports split-based transfers. They have MUX against supporting the FlexBus, and power management was implemented in both. Also, the RAS for reliability, accessibility, serviceability was defined for both. And retimers was pulled over from PCI Express standard. And this outlines the CXL up to 1.1. When it comes to CXL 2.0, CXL 2.0 specification added the switching function, memory pooling, fabric management, and security. So I think the most important features added to CXL 2.0. Let's talk a bit more into those features in CXL 2.0. The switching is very similar to the PCI Express switching, as it enables one link to be expanded to multiple links for wider fan-out, and also has the functionality of memory interleaving within CXL structure, which is an interesting capability. The resource pooling that allows flexibility and how your system is configured dynamically over time. So for example, memory pooling and IO devices can be assigned to one application and then one configuration at a given time, and then change or reallocated now based on the workload. And that's supported by the fabric management. It's the third bullet here. Unique feature about this is that there's a standardized configuration and error reporting, given some coding templates that have been developed so that the fabric management software does not need to be completely implemented from scratch by each vendor. So that should add a lot of standardization and commonality and reliability to the overall system. For security, as I mentioned, CXL has co-opted the integrity, the data encryption IDE/IDE standards from PCI Express to prevent malicious snooping from end-to-end on the communication link, all the way down to the very lowest level of wireline. Comes to CXL and EP enumeration, the CXL enumeration for endpoint was simplified to be more like the original PCI process. So there's a compatibility here now. And then has a general term cache and memory enhancement to enable new functionality and better operations. So it definitely helps with persistent memory. The error reporting has been standardized, and it adds improvements to the hot plug and quality of services as well. And I had mentioned earlier as well that CXL 2.0 is a fully backward compatible. Let's talk about the three CXL protocols. Just like there's been three standards, there are three sub-protocols defined. They are CXL.io, CXL.cache, and CXL.memory. CXL.io is a unique because it crosses the PCI Express and CXL boundary. Actually, the packet is more like a PCI Express packet, and this used for the device enumeration, programming, register access, and things like that. And every CXL device must implement the CXL.io or their own function. CXL.cache has a different application. It allows the CXL device to efficiently access the host memory. It allows the device to get quick access to the host memory. And CXL memory is just the opposite of that, or at least conceptually, as it allows the host to get direct access to the device memory or cache. So they are complementary function. I think the next slide will highlight that. Now let's talk about the CXL device types. As we know, there are three CXL standard versions, three CXL sub-protocols. Similarly, we have three CXL device types defined within the standard. They have type 1 device, which are our NIC and accelerators with the cache. Type 2 devices, which are accelerator with memory and cache. And then there is a type 3 device, which is really targeted for a memory expanders. And it has no acceleration capability. There's no processor for acceleration in type 3 device, unlike the type 1 and type 2 devices, which will have some local processing power to perform specific application requirement. If we look down to the diagram here, over to the left, there is a type 1 device, and you will see there's a direct communication between the CPU memory and the device cache, and is controlled by the device cache or by the device itself. And to implement that, you need type 1 device to implement the CXL.cache sub-protocol. If we now jump over to the right-hand side here for a type 3 device diagram, you will see that in this case, CPU is directly accessing the memory content of type 3 memory expander card. To do that, it uses the CXL memory of a sub-protocol. And then in the middle, is the type 2 devices, which actually combines the two and uses both of the sub protocols. And the one note we should consider here is CXL IO is basic to the communication with all CXL devices. CXL IO is also special in that it shares 128 bit of a standard 130 bit PCIe packet. This slide here is on the legal CXL configurations. CXL defines a native primary port that's 32 giga transfer per second and can have a link width of either 16, 8, 4, 2 in CXL version 2.0 specification. There is also a definition for native mode bifurcation. For 32 giga transfer per second, port can be split into 2 independent links of 8 lanes each, or 4 independent links of 4 lanes each. Then there's the degraded mode of operation. And in my opinion, these are really intended mainly for debugging the customer's 32 gig port at 1 lane each. There is also a 16 gig transfer per second at 16, 8, 4, 2, 1 lane. So there may be some product opportunities there, but as of now, mainly used for the product bring up. The next one is the CXL Protocol Overview. In this section of presentation, we will dive a little deeper into the CXL protocol aspects. First, let's go through some of the key features of CXL, like what makes CXL run over the PCIe Express PHY and electricals, and then talk about how you can use the Xgig protocol analyzer to analyze the CXL link. So let us start with how CXL devices connected to a system. The slide here shows a simplified slot implementation of the FlexBus port on the left-hand side. Here, the FlexBus design allows to choose between the native PCIe protocol or the CXL over the PCIe 5.0 electricals. So as shown on the picture on the left side, you can actually plug in the CXL card or the PCIe card into a flex port. And depending on which card is plugged in and detected on the slot, the appropriate protocol is selected. Now, the selection of the protocol takes place during what is called the LTSSM process, shown in the right-hand side. Clearly, the LTSSM is defined in the PCIe specification. And when PCIe card is plugged in, it goes through various phases or states of the LTSSM and gets into the L0 state and start communicating in PCIe protocol. But when a CXL device plugged into the same flex slot, the root port negotiates the CXL protocol. So what is called an alternate protocol negotiation process. The negotiation process also happens during the LTSSM, and the link bring up has CXL at L0, and they start communicating in the CXL protocol. Now, one interesting thing here is because of the flexibility of the FlexBus design, this allows analyzer or inline test tool companies to use their current existing PCIe 5.0 test equipment on the CXL link. You can use the VIAVI Xgig PCIe 5 chem interposer, for example, on a FlexBus port to capture and analyze the CXL bringup. So here we look into how the PCIe versus CXL mode of selection happens. Once you apply power to the PCIe 5, it goes to state as shown in the slides to go to L0 or normal communication. Now this is a simplified version of the LTSSM. I'm just showing the main states here, and the 5 goes through the detect, polling, configuration, and out to L0, and optionally goes through the recovery depending on the what speed it support. The detect state will detect if there is a far end termination, or in other words, if the device is present on the other side of the link. If it got the link partner to talk to once, the detect phase is done. The LTSSM link state enters the polling where it receives and transmits training sequence or training order sets like TS1, TS2s for a PCI device, and it establishes bit lock, symbol lock, and other lane polarity, etc. during this phase. Once it's done out of polling, it gets into the configuration phase where it negotiates the link width, speed, EQ option, which are like it will either bypass the equalization or go through the full equalization. And once it is done, it knows both the link partner knows the capabilities of each side, and the link enters the L0 Gen 1 side, and then moves the IR speed if both the link partners agrees upon. When you plug in a CXL card, the same exact process goes through. It moves through the detect, polling, configuration, but right out of the exit, if it is a CXL and if you are on a flex bus, you will notice what is called a modified training sequence instead of a regular training sequence. The modified training sequence giving billing partner capability to negotiate CXL protocol spec and write protocol specification capabilities that either side of the link can support and enable the link. And once it's out of the configuration phase, it has established CXL and it will move on to L0 at Gen 1 and perform the recovery to IR speed if both the link partners agrees upon. In both cases, the PCIe and CXL devices, once it enters the L0 state, it both transmit what is called an SDS, start of data stream order set. Then followed by that, it transmits logical idles on the PCI link and null packets on the CXL link. That triggers the start of the protocol data or the actual transmission to the protocol communication of the link. One thing to notice here is to operate at CXL mode, the link speed of the CXL link on the PCIe 5 should be at least 8 gigatransfer per second. If the link is unable to transition to the 8 or IR speed, that is Gen 3 or IR speed, even after establishing the CXL mode during the configuration phase, even after establishing CXL protocol, the link may ultimately fail to come to 0. Now we see how a trace capture looks when CXL bring up happens. Right now on the screen, you are seeing is a snapshot of VIAVI Xgig capture on CXL bring up. And on the left hand side, you are looking at the screenshot or snapshot of the trace capture on the Xgig analyzer. And on the right hand side is the LTSSM states as represented by this. So the capture can be taken, and then you can look at the LTSSM states for that capture. And so similarly, you get the detect state, the polling state, and these are the substates of the configuration phase. What we want to highlight here is how the protocol is negotiated during the substates after the link width, lane width, link and lane width negotiation and the speed options provided by both sides. Then you go on to the actual negotiated protocols. And the alternate protocol here is CXL. And up here you can see this is the downstream side on the left column and upstream side on the right column. The downstream port then comes up and says, okay, I'm capable of CXL.memory and CXL.io. And then the upstream port look at that and it advertises its capabilities. They also share its version available, CXL memory capability, CXL IO capability. Once they advertise their capabilities, then the downstream port will come up and enable at the common capabilities in favor. So here you will see that MEM and IO are enabled on this link. Once they transition from TS1 to TS2 phases, which is a second type of training sequence, then they move on to L0, which is the normal traffic. So the idea is to follow the same states of LTSSM, whereas using the modified training sequence on the CXL link. You will notice that it can negotiate the various capabilities on the devices. We are showing here the actual bits with the modified TS1 and TS2. As I said, modified TS are new fields defined to negotiate CXL. On here, you can see the alternate protocol is set to CXL, and there is something called alternate protocol status. The status indicate in this case requesting is request pending, which means that downstream indicates that protocols are supported and it's waiting for the upstream to confirm that these protocols are also supported by the upstream. Then the upstream comes up and gives its advertisers its protocol capabilities that again like the 2.0, the version 3 capabilities. Whether the card is also capable of PCI, etc. Then once they exchange their protocols and the downstream come up and enables them. So here you can see 2.0 is enabled, .mem, .io is enabled. .io is always mandatory protocol for all types of devices. So you will mostly see that it is always enabled. But one thing to notice is one side doesn't support capability 2.0 and other supports 2.0. So 2.0 is not enabled on this link. So we know that the link will go to the L0 and will talk in 1.1 protocol version. Once the link gets into L0 phase, they send out what called start of data stream or the SDS order set. And then following the SDS order set exchange, they send out what are called the null fleets. The null fleets are a unit of transfer on the link. We'll talk about what it looks like later. But as of now, just consider these are null packets on the link layer. The upstream and downstream both sends out null fleets after they sends the SDS. And in order to transition to L0 phase, at least 4 null fleets are needed. So once they transit, they go through the LTSM phases, get into L0 transmitter, and once they transmit enough null fleets, there will be a regular CXL traffic conversation between the root complex and the host. Null fleets are also inserted into the data stream by physical layer when there is no valid fleets available from the link layer. These are synonymous to logical idle events on the PCIe express. Okay, so that's what the whole process of CXL bring up looks like. Now we move into the hard MUX layer. It is a new layer in the CXL stack or the Flex Bus stack. The right you see the figure shows the Flex Bus layer stack. On the bottom of the stack is the Flex Bus physical layer, which supports both PCIe and CXL protocols. And then up here the CXL link layer and the CXL transaction layer. The link and transaction layer have two logic cores, a subdivided logic cores. One that handles the .io and other logic core handles the .mem and .cache transactions. There are multiple link layers right here, and then multiple link layers interface with the physical layer to what called the MUX layer that's shown in orange in the figure. So MUX layer provides dynamic muxing of the .io, .cache and .mem link layer controls and the data signals, and provides an interface between the link layer and the physical layer. So in the transmit direction, where MUX layer arbitrates between the various link layer and forwards the CXL packet from this link layer to the physical layer media, and received direction, they are MUX protocol associated with each other of the packets coming up from the link layer, which are flipped and pass them back to the link layer. So it is the interface basically to multiplex various link layer packets and send them onto the physical layer. And in addition to forwarding these bits or packets, it also maintains a link layer state machine and processes state transaction requests from this various link layers to the physical layer. And then the responses are processed and sent back when the other side updates its state machine. When we compare this MUX layer with PCIe, the PCIe transaction do not have any MUX layer, and it is bypassed in the PCIe. Now let us look into the MUX packet. The communication through MUX layer happens with two types of bits. One is called the request bit, the other is the status bit. The top two lines that are colored in blue up here are the request split. An ALMP request split stands for MUX Link Management packet. And those are the request split that initiate any state transaction, and the responses are used to communicate the current state of the remote part. So the responses are done in the pink, the second two rows on the screen. The ALMP packet has one D word. So you can see up here highlighted in the same D word is repeated. And the same D word is repeated here 4 times within the fleet. This is done to provide the data integrity protection. MUX layer obviously provides very important role in keeping the states and forwarding fleets back and forth between the layers. So from here, we will move to the CXL protocol analysis. So we will cover CXL cache memory transaction analysis, CXL triggers, some real-time metrics, and CXL trace analytics using Xgig protocol analyzer. Here on this slide, we'll talk about this different CXL transaction. Let's take an example of CXL.cache. A very simplified figure here shows us the CXL cache devices such as an accelerated connected to the CPU. The host CPU has the host attached memory and is talking to the CXL device for the CXL link. Of course, there is also a .io CXL link is available. The .io line between the host and the CXL device is not shown in this picture. The CXL.cache link or the protocol allows coherent access between the device's cache and the host attached memory. So the protocol will let the CXL cache device directly cache the host memory with extremely low latency, and it does that by using the request response approach. So in this case, there are 2 directions defined by the spec for a cache transaction. Those are S2D and D2H. S2D stands for the host to device and D2H stands for the device to host. And as you can see, there is a request response and the data in both directions. S2D and D2H can send request and response to each other. So let's look at the D2H request first. The D2H requests are requests from the device to the host, typically targeting the host memory. The request cacheable access through the reads or writes on the link to the host memory. The S2D response will carry the requested data back along with some ordering messages. The S2D requests are usually snoop requests to maintain the coherency by checking the cache state and changing the cache state of the device if needed. And the device responds to these snoop messages and indicates any state change as well. Provide the return data to the host as requested. Let us go to the memory protocol now. The CXL memory protocol also is a way of connecting the host CPU to the device memory, such as the memory expander. There is a device attached memory, of course, and there is a host attached memory. The memory protocol is a transactional interface between the CPU and the device memory. Here, it lets the host map the device memory into the system memory, and it allows for a different type of memory attached option, including memory controllers, accelerators, devices, and expansion devices. There again, there are 2 different directions defined here. One is M2S and another one is S2M. M2S stands for master to subordinate and the S2M stands for the subordinate to master. And the host is the master in this case, and then it can send out the request. The host is the one that initiates the request with or without the data, and the subordinate, which is the CXL device, with attached memory response again with or without a data depending on the request. So you can look up here, there is a host in the device which can send push memory read or memory write out to the device, and the device gets back with the requested data. We see the same on the slide here. The memory read and the memory data coming back in the fleets back from the device to the host. So that's the memory protocol again. A fleet, like I said, has a header and 4 slots. And we looked at various type of headers. The spec defines the slot formats that puts this header into certain combinations. A device look up to these slot formats and applies one of the headers into the header, or it transmits the header in one of the slots. So what this gives is the ability for the device to have a multiple transaction and push multiple header data in response to the same bit. So here in the diagram on the left side, you can see slot 1 has 2 headers, slot 3 has 3 headers, and slot 2 has 2 headers. So in order to make the transaction tracking easy within the analyzer, we added the ability to split a transaction, look at the multiple sets. This is covered across all the protocols on the VIAVI Xgig platform, but also slot by slot decode that gives you this log format and the individual header that go along with the slot. And the latest and the most unique part of the platform is that we had additional tags on each header basis. So if you have, say, 10 headers going through fleets, based on these tags, you can actually individually track these headers as being part of a transaction. So for example, there is a data header going through the slot 1. Because of additional tags we added, we know it's from a dirty event sent by the device. And there is an CQID of 1C0 and UQID of 122. So it also tags them particularly to a transaction, which makes it very easy then to track this multiple transactions simultaneously. So here we shows the different trigger formats available with the CXL analyzer from VIAVI. The trigger capability from the analyzer allows you to trigger on any CXL fleet types, but also it allows you to trigger on any of the headers, slots, and the tags inside the header. So you just need to drag and drop the packet you are looking for from the middle column to the right side to the left column to the flowchart. Comprehensive metric performance and protocol analysis capabilities with Xgig analyzer. There are real-time metrics that are looking to count different type of splits, look at the throughput of the splits, but also errors can be real-time monitored with fleet CRC errors, null fleet errors, incorrect protocol IDs, as well as LCRC errors between the TLPs of the .io fleets. TLPs and the .io fleets can be monitored. In addition to the real-time metrics, there is a full suite of post-capture analytics tools that can provide timing and graph for protocol spec violation. The spec defines many thresholds, and if the thresholds are not met and have like a direct access to all the flags that the threshold violations are caused, then there is a transaction statistics. But not just the transaction agents, we also have the agents split by the data time, response time, comment to the data, etc., as well as per transaction statistics, and the things are available for performance as well as the protocol analysis. In this slide, we talk about the Serialytics for CXL, a tool, post-process analysis tool available in the Xgig protocol analyzer. This is the latest addition to our platform called as Serialytics. It gives you a trace analytics for the CXL protocol. You can look at the trace counts, the heat map, and any anonymous event that are causing a disruption to your CXL link here. I'll just take a minute to explain about the different products, protocol analysis products available with VIAVI for CXL protocol analysis. So here in this page, you'll be seeing a different protocol analysis tools available with VIAVI for 32 gig giga transfer per second. On the left-hand side top, you are seeing the 16-lane 32 gig transfer protocol analysis tool, which can be used for both PCIe 5.0 and CXL 2.0 traffic analysis, traffic generation, protocol compliance, and protocol inline error injection. And on the left-hand side, the bottom, you will be seeing a by 8 32 gig transfer per second analysis tool, which can be used for both PCIe 5.0 and CXL 2.0 protocol analysis, traffic generation, PCIe SIG, and the CXL Consortium compliance, and both the by 16 and the by 8 lane width hardware are backward compatible. That is, it supports all the lower lane width and the older generation of the protocols. On the right hand side, you'll be seeing the by 16 CHEM interposer and a test stand for the compliance. We also have an interposer in other form factors like by 8 CHEM interposer, by 4 CHEM interposer, M2, U2, U3 as listed in the presentation.
So we have the CXL license options available for existing PCI analyzers and license it as analyzer accessories and analyzer and accessories. So that's end my presentation. Thank you. If you have any questions, I will be on the panel. Questionnaire. Please drop your questions. We'll try to answer it as soon as possible.